Okay, so good afternoon, everyone. I am Keshav, currently research scholar at IIT Kanpur. So I will be taking this. So I will be taking this problem solving session for week 9 of NPTEL course ME111, which is applied numerical methods. Okay. I hope I am clearly audible. So before going to the content that has been covered in week 9, let us revise whatever has been discussed in week 8. Okay. So in week 8, what we have seen? In week 8, we have seen the numerical solution of partial differential equations. Okay. Partial differential equations. So there we have seen 1D unsteady heat conduction problem. Okay. This problem we have solved using 3 methods. First one was what? Explicit method. Second one was implicit method. And third one was Crank-Nicolson method. Okay. So we have also done the stability analysis using the von Neumann stability analysis, model analysis that can be used for linear system. And by doing the stability analysis, what we have found that this explicit scheme is conditionally stable, while the implicit scheme and Crank-Nicolson scheme was unconditionally stable. Okay. So what we mean by stability? Stability means if random errors that generated in simulation if it grows with respect to time, then system is called a what? Unstable. Okay. System is called unstable. And how this random error is generated? In computer, there is round off error. So this round off error, suppose I am writing √2 in computer, so it will write 1.414 dot dot dot. It will go to the infinite number of terms, but it will store till some decimal place. So this is what is called as round off error. This is kind of random error. And if this random error grows with respect to time, then our simulation is what? Our solver is unstable. Otherwise, it is stable. Okay, fine. So suppose at some nth iteration, we have epsilon is a round off error. At n plus 1th iteration, at some ith location, the round off error is epsilon I at n plus 1. So if we take the ratio alpha, which is growth factor or amplification factor, that will be equal to epsilon I n plus 1 divided by epsilon I at nth iteration. If this is greater than 1, if alpha is greater than 1, then our system is unstable. Otherwise, it will be stable. Clear? Now we'll move towards the week 9. This week, so if we consider any physical problem, if we wish to solve that problem, first what we'll do, we will convert this problem into equations. Okay, this conversion of physical problem to equations or mathematical model is known as model building or mathematical modeling. Okay. Then once we have the equations, then this equation can be solved. Then the solution of the mathematical model or the set of equation is called as simulation. This simulation can be done in computer, or we can do hand-based calculation if the analytical solution is possible. Okay. Once we solve the problem, we validate whether our solution is correct or not. Okay. So in general engineering application, this set of equations that we got, they are either ordinary differential equation or partial differential equations. Usually what we do, we take some assumptions, some set of assumptions to convert this physical problem into a ordinary differential equation. This is kind of simpler one to get the bigger picture of the physical problem. Okay. And once we solve this ordinary differential equation, to get the more details of the big picture that we got from the ordinary differential equation, to get more details, we relax some assumptions and go to partial differential equation. Then this equation that comes, that is partial differential equation, that give more detail of the physical problem. Okay, clear? Just response whether I am clearly audible or not. Okay. So sometimes what we have, these equations that we convert during the mathematical modeling, the physical problem that has been converted into the equations. Sometimes we do not have the equation, but we have the data, but the equations are unknown or unusable. In that case, by using the existing data, we build a data-driven model. That data-driven model is called, this building data-driven model is called regression and optimization and all. Okay. So before going to the physical problem, let us rewind or recap one problem that has been discussed in week 1, the payload delivering using parachute. Okay. So if we consider, suppose we have this mass m of payload that we wish to deliver at some location. This location may be the flood affected area where we want to supply some essential goods like that. So the basic model can be, so what we are doing here, we have some mass m that we wish to deliver. So what we're doing, we are dropping this mass using a parachute. Okay. So the simple or basic model can be, we neglect the parachute. Then what will happen? There is only one force acting on this mass, that will be mg. So this, from Newton's law, ma will be mass multiplied by acceleration will be equal to mg. This acceleration can be written m du upon dt. So this will be my differential equation. And we know the initial condition that mass has been dropped. So at that case, at t is equal to 0, our velocity is 0. Okay. So we wish to find the velocity when it hits the ground, because there can be a limitations on the velocity. Since if the velocity is very high, this whatever the payload that we are delivering, due to the high velocity of impact, it may be destroyed. So we want to restrict the velocity up to some level that can come from another set of analysis. So we want to restrict our velocity at u naught when it hits the ground. Okay. So from here, that was a basic model. If we go for an improved model, which means we consider the effect of the parachute also. When we consider the effects of the parachute, then a drag force will also come that will be proportional to the velocity square. Okay. So in that case, what will be my differential equation? My differential equation will be dm du upon dt, that will be equal to mg minus the drag force cu square. Same initial condition we have and same limiting velocity. Okay. So in that case, there exists a terminal or steady state velocity. Okay. When this will come, when our acceleration will go to 0, in that case, the payload will have a constant velocity that is known as terminal velocity. So simply I put here du upon dt equal to 0. At that case, mg minus cu square, that will be equal to 0. That will lead to u will be equal to mg divided by c under root. This is what? This is my terminal velocity. Okay. So suppose this, whatever the payload delivery problem we have, we wish to solve this problem numerically. So what we want to find? We want to find u naught at various t naught. Okay. U naught at various t naught. So this problem can be converted into a system of ordinary differential equations. The first differential equation can be dm du upon dt will be equal to mg minus cu square. Given the initial condition, u at t is equal to 0, 0. And also we can have another differential equation, dh upon dt, that is height, that will be equal to u, and u at some time t naught is equal to h naught. So we will solve this problem till h goes to 0. Okay. So these two are uncoupled ordinary differential equations, which is nothing but an initial value problem that can be solved using fourth order Runge-Kutta method, like we have solved in week 7, I think. In week 7, we have discussed this kind of problem, the predator and prey type of problem, or the population where population and resources depends on each other. So population increases like that, then decreases, then again increases. Similarly, the resources has some this kind of distribution. Okay. Now, if we solve this problem, somewhat this we will get the solution. Okay. So once we consider the effect of parachute, the velocity will first increase, then after some time it will become constant, which will be equal to terminal velocity, and height will decrease continuously. Okay. Similarly, if we do not consider the effect of parachute, our velocity will constantly increase. It will increase constantly. Okay. And height will decrease more and more since the velocity is increasing. So slope of this height will increase continuously. Okay. This was the revision of the problem that has been discussed in week 1. So now we're going to consider a problem, heat transfer in a nuclear rod. And by seeing this problem, we will first what we'll do, we'll see this problem. This is a physical problem. Then from here, we will do the mathematical modeling to get the equations. Once we will get the equation, we will do the we will solve it, or we will get the solution by doing the simulation. Okay. This simulation is nothing but numerical analysis. What do we, so in numerical analysis, what we'll do? We will discretize the equation. Sorry, we will discretize the equation. Then we will discretize the boundary condition equation. Then we will discretize the boundary condition. Then we will use the appropriate numerical solver to get the desired solution. Okay. So by heat transfer means what? We want to study the heat conduction. Okay. So this is the heat conduction equation. This is general heat conduction equation. This is the energy in the control volume, rho ut del upon del T of rho Ct. That will be equal to the heat going out from the control volume, from the control surface, and plus rate of heat generation in the control volume. Okay, so this is the heat conduction equation. So if I consider the constant property, if I consider the properties as constant, this rho c can be taken outside of this differentiation. So rho c will come out, similarly k will come out. So this is what equation we will get: rho c del T upon del T, that will be equal to k, that is thermal conductivity, multiplied by Laplacian of T plus Q triple prime. Okay. So in 3D Cartesian coordinate, this Laplacian can be represented as del u upon del x square plus del u upon del y square plus del 2 upon del x square plus del 2 upon del y square plus del 2 upon del z square. If the problem is steady state, then my temperature will not change with time. So this will be equal to 0. In that case, this is the equation that we'll get. So if I write this equation in 2D steady state form, so this Laplacian can be written as del 2 upon del x square and del 2 upon del y square. So our equation will be this. Okay. Now boundary condition. So boundary condition can be of three types. First is Dirichlet type boundary condition. In Dirichlet type boundary condition, we specify temperature at the boundaries. Means what? The temperature as the boundary is some T infinity, which is known. Okay. If the temperature is specified, in that case, the boundary condition is known as Dirichlet type boundary condition. And then another type of boundary condition can be Neumann type of boundary condition. In Neumann type of boundary condition, we know the derivative or the gradient at the boundary. Okay. This can be also said as specified flux, since from the Fourier law of heat conduction in x direction, if I write heat flux, that will be equal to minus k del T upon del x. This will be equal to the heat flux in the x direction. Okay. So I hope you are able to hear me. So Neumann type of boundary condition, by using the Fourier law, we can write like that, which means it can be said as specified flux heat condition. Okay. Now, if my boundary is insulated, or we have some geometrical symmetry, geometrical and mathematical symmetry, in that case, suppose I have the insulated boundary condition, then the flux will go to 0. In that case, del T upon del x, that will be equal to 0 at the boundary. So first one is Dirichlet, second one is Neumann, third one is what? Robin type of boundary condition. So Robin type of boundary condition is also known as mixed type of boundary condition. In that, we get the gradient of temperature is a function of temperature. Okay. So this is known as Robin's type of boundary condition. This typical type of boundary condition we get when we have convective boundary condition. Okay. So let us come back to our problem, which is heat conduction in nuclear rod with heat generation. Okay. So suppose this is my nuclear rod, which is long, and it is convecting the heat from the surface. Okay. This is the cross section area of the rod. I am considering this dimension is very long compared to the cross sectional dimension. In that case, what will happen? Suppose I am writing del upon del z. Okay. When this z will be large, then this overall derivative will go to 0. So we can consider only the gradient in the temperature will exist in the transverse direction. Okay. So this is the enlarged view that I have drawn here. So in x direction, we have 2L dimension, which means if I take the axis x and y like that, so my x will change from minus L to plus L. Similarly, my y will change from minus L to plus L. Okay. So this is my problem. And the governing equation for this problem is what? This is the governing equation, del 2t upon del x square plus del 2t upon del y square. That will be equal to minus q triple prime upon k. Q triple prime is what? Heat generation per unit volume. Okay. So before going further, let us non-dimensionalize this equation. So how we can non-dimensionalize this? First, let us dimensionalize the length scales. So I am assuming as x star is equal to x divided by L. Similarly, I am assuming y star is equal to y by L. From here, what will they get? This delta x will be equal to del x will be equal to L multiplied by del x star. Similarly, del y will be equal to this. Now you put this, then this is the equation that we'll get. Here the term L square will come. If we take L square in the right hand side, so this is the equation that we'll get, del 2t upon del x star square plus del 2t upon del y star square, that will be equal to minus q triple prime L square upon k. Okay. So now if we assume theta will be equal to T minus T infinity is the surrounding temperature. If we assume theta like that, this is the equation that we will get, del 2 theta upon del x star square plus del 2 theta upon del y star square will be equal to minus 1. So you see here we do not have many parameters. We only have theta, x star and y star. So we have reduced the number of parameters by non-dimensionalizing the equation. Now we will see the boundary condition. So for the boundary condition, we need to do the energy balance at the boundaries. Okay. So suppose this is my computational domain. Okay. This is my computational domain. This is my boundary. Okay. This is my boundary. This is my boundary. So boundary is physically boundary is what? Zero thickness. Boundary is having zero thickness. So I am just enlarging the boundary and showing some thickness here. Okay. Actually boundary do not have any thickness. So at this surface, there will be unit normal vector, area vector or unit normal vector. Similarly, at this boundary, at this section of the boundary, there will be a unit normal vector n2 hat. By the convection, this unit normal vector will go outside of the surface. Okay. I am assuming some q1 is coming in from this surface. Similarly, some q2, here will be q2. Some q2 is coming from this surface. Okay. So by doing the energy balance, control Z. By doing the energy balance, we can find out the boundary condition. Since the boundary do not have any mass, which means what? The boundary cannot store the energy. So if it will not able to store the energy, whatever the heat will come from this surface or this surface, that will go out from this surface. Or if we take the summation of the energy across the control volume from this small control value, that will be equal to 0. Okay. Whatever is coming in, that will go out also. So across the area, I am doing q and cap dA, that will be equal to 0. So here only two cases here. So from here, q1 coming and area is outside n1. So that will be equal to minus q1 dA. Similarly, if at this surface, it will be minus q2 dA. That will be equal to 0. From here, we can write that minus q1 minus q2, that will be equal to 0. So what is q1? Q1 is from interior surface. Now, so it is coming from the conduction. So from the Fourier law of heat conduction, we can write Q1 will be equal to minus K del T upon del X. Qt is what? Qt is convection, that is going, Qt is convection. So it is flowing from this direction to this direction. Here temperature is T infinity, at the wall temperature is suppose T. So that will be equal to H multiplied by T infinity minus T. So this is what I have put here. Now we can take minus common. So this is the what? This is the equation that we will get. So this is the boundary condition. So now if we use the same theta and delta x, sorry, x star, we non-dimensionalize it, then this is what we will get. We will get del theta upon del x star plus bi theta equal to 0. This bi is what? This bi is bio number. This bi is bio number that will be equal to h L divided by K. L is what? Length scale. H is what? Convective heat transfer coefficient. K is thermal conductivity of the material. Okay. Now, what is our mathematical model? So, governing equation will be what? Del 2 theta upon del x star square plus del 2 theta upon del y star square. That will be equal to -1. And boundary condition x star equal to plus -1. We have this boundary condition. Similarly at y star equal to plus -1, what will be the boundary condition? Same, only x star will be replaced by y star. Okay. Now we'll see, if you see here same boundary condition, here same boundary condition. Similarly, here same boundary condition, here same boundary condition. Okay. So if I consider this section and this section, whatever will be the solution here, the same solution will be in this section also. So I can assume this as a line of symmetry. Okay. By assuming the line of symmetry, I can neglect the lower part and consider only the top part. While I will do this, I need to put the boundary condition at this surface as del theta upon del y star, that will be equal to 0. Whatever will be temperature here, the same temperature will be this side, means what? At the boundary, there will be no gradient. Okay. Similarly, in the x direction, if you there is symmetry, so this part, this maybe I should change the color of the pen. So this part can be neglected. Similarly, we have neglected this part. So the actual that has been come here is the 1/4 of the actual dimension. Okay. So from the symmetry, when we can consider the symmetry, when there is geometrical symmetry, there is a symmetry in the boundary condition, and our differential equation is linear. Okay. Differential equation and the boundary condition is linear. Then only we can assume the symmetry. Okay. By considering the symmetry, this is the boundary condition that we got. Now, this equation is known as a Poisson's equation. Okay. Poisson's equation. So now we'll see how to solve a Poisson equation. Okay. So in general, a Poisson equation can be written like that. Laplacian of u will be equal to f. Okay. So in the 2D Cartesian coordinate, I can write del 2u upon del x square plus del 2u upon del y square. That will be equal to, in general, it can be function of x, y, and u. Okay. What will be the homogeneous form of this equation? The homogeneous form of Poisson's equation. The homogeneous form of the Poisson's equation is called as Laplace equation. Okay. Now let us discretize this Poisson's equation. So we assume delta x equal to Lx divided by nx minus 1. Similarly, delta y will be equal to Ly divided by ny minus 1. So we are considering nx small section in the x direction and ny small section in the y direction. Okay. So this is how our grid will look like. Okay. So x is starting from 0 going to Lx, means what? I is starting from 1 and going to nx. Similarly, y is starting from 0 going to Ly. Similarly, j is starting from what? 1 and going to ny. Okay. So this is my what? Suppose I am writing this is my I comma j location. So the just above it, it will be I j plus 1. Just below it, I j minus 1. Just left to it, that will be I minus 1j. And just right to it, that will be I plus 1j. Okay. So this is our governing equation. So let us what do? Let us discretize this governing equation. So the second order derivative, we can write like that using the central difference method. So this will be equal to del 2u upon del x square will be equal to ui minus 1 j minus 2 uij plus u I plus 1j divided by delta x square. Similarly, del 2u upon del y square we can write, and here right hand side f I comma j. Okay. So if you see here, there is one term of u I minus 1, one term is j minus 1 term is I plus 1, another term is, sorry, j plus 1, similarly a j plus 1. So we have 5 terms. One, so there will be, if I write this equation in simpler form, that will be equal to aij minus 1 multiplied by uij minus 1 plus ai minus 1j ui minus 1j plus aij uij plus ai plus 1j ui plus 1j plus aij plus 1 multiplied by uij plus 1, that will equal to fij. Okay. So this aij minus 1, that will be equal to aij plus 1, that will equal to 1 upon delta y square. Similarly, this also can be written, and aij will be equal to minus 2 divided by delta x square minus 2 upon delta y square. So this is what? This is what? This is a linear equation. So at every ij, if we write the equation, we will get a system of linear equation. We will get system of linear equation. So this is my system of linear. So what we have done? We have converted a partial differential equation into a system of linear equation. Okay. So if we write this A is what? At in every equation, A has 5 terms. 1, 2, 3, 4, 5 terms. So this is what? This is a pentadiagonal matrix. So for every equation, these all terms we have, the terms that we are seeing, nx multiplied by ny term, all terms we are seeing in equation, in this equation. Only there is one thing, coefficient for other gate point is 0 except these 5 points. Okay. So if we write this A matrix, this is A matrix is what? Large matrix M cross M, where M is what? Nx multiplied by ny. And this is a sparse matrix. Why sparse matrix? Because it contains lots many zeros. Okay. So how many zeros? Number of terms M square minus 5, because each equation can have maximum 5 non-zero values. Okay. So this is the pentadiagonal matrix. So the tridiagonal system solver, which is a Thomas algorithm, that we cannot use to solve this problem. The direct solver, Gauss elimination like solvers, we can use, but it is not efficient. Why not efficient? Because it involves lot of calculations. It involves lot of calculation, and also there is one major drawback, that it will not preserve the zeros. It will not preserve the zeros. Means what? The matrix that we have the sparse, maybe after first or second iteration in the Gauss elimination, that will not be a sparse matrix. So that will be a computationally extensive process. So what we can do? We can use a iterative solver here. Okay. So iterative solver will preserve the zero and will also have a less calculation. Okay. So let us revise the iterative solver that can be used to solve a system of linear equations. Okay. So let us recap the Jacobi iteration. So suppose we have the linear system A equal to B. This can be also written as j equal to 1 to n aij uj, that will equal to bi, where I goes from 1 to n. So this system of linear equation can be written like that. Okay. So what we do in Jacobi iteration, from the first iteration, we keep u1 in the left hand side, rest we send to right hand side and get the u1 from the first equation. Okay. So u1 of k at some kth iteration, that will be equal to b1 minus j will go from 2 to n aij, sorry, a1j, because we are writing for the first equation, a1j uj at k minus 1th iteration. Similarly, if we want to write the u2 at the kth iteration, so these term will remain in the left hand side, other will go in right hand side. So it will be equal to b2 minus this term a21 u1 at k minus 1th iteration plus j goes from 3 to n u2j, sorry, a2j uj at k minus 1th iteration. So in general, we can write u at ui at kth iteration, that will be equal to bi minus j will go from 1 to n, except j will not be equal to I, aij uj at k minus 1th iteration divided by aii. Okay, this can be written like that. Okay, I am simply adding aii ui at k minus 1 and subtracting it. So that will lead to this equation ui at kth iteration, that will be equal to ui at k minus 1th iteration plus ri divided by aii. This ri is nothing but the residue RHS minus LHS at the k minus 1th iteration. Okay, so this can be written as ui will be equal to ui at previous iteration plus some correction. Okay, when this correction, this residue, when this residue will go to 0, then this correction will also go to 0. Then in that case, our solution will go to the exact solution. Okay, so what we are doing here, suppose I am calculating the value for the second equation. So I am using here the value of u1 which is known for the kth iteration, but we are using the previous value. So in Gauss-Seidel, what we do, in we use the latest value of uj to find out the rj. So equation will remain like that only. ui at kth will be equal to ui at k minus 1th plus correction. That correction will be equal to ri divided by aii. But this ri will be equal to bi minus j will 1 goes from 1 to I minus 1. There we will use the value of uj at kth iteration plus the unknown values we will use at k minus 1th iteration. Okay, so this is what my rii. So to improve the solution, we can use the successive oval relaxation technique. If you remember, we have discussed this in week 4 or week 5. So in that case, we multiply with some w in our correction. This w is some positive number. Okay, if this w is equal to 1, this is called as classical Gauss-Seidel method. If this w is greater than 1, then it is known as over relaxation factor. What it will do, it is used to speed up the convergence process, but sometime it may happen that solution may diverge. This we have already discussed in earlier week. Similarly, to stabilize the solution, we can use W between 0 to 1. This is known as under relaxation factor. Generally, the commercial software that are available, they are using the Gauss-Seidel method. They are under relax. Okay. Now let us discuss the boundaries conditions. So boundary condition, to at x equal to 0 means what? I equal to 1. We have del theta upon del x equal to 0. Means what? Which condition? This is the, suppose this is my domain. So this is my x equal to, sorry, x equal to, no, this is my x equal to 0 line. Na? This is my x equal to 0 line. So here I want to write the boundary condition. Here I want to write the condition. So in this side, we do not have a grid point. So what we'll do, we will use the 2 point, forward difference scheme to calculate this gradient. Okay, sorry, forward difference scheme to find out the gradient. So this is what, so here we will use ui plus 1 j minus theta uij divided by delta x will be equal to 0. From here we will get this. Similarly, at y is equal to 0, if I write, that will be equal to theta I j plus 1 minus theta I j divided by delta y. This will be delta y. This will be delta y. That will lead to this equation. Okay. Now similarly, at x equal to 1, if I write the boundary condition, this is my boundary condition. So now this gradient will be written as a backward difference. Since at this point we do not have a grid point in this side, so we will use this side of grid point. In that case, we will use the backward difference scheme. So we'll write the gradient like that. That will lead to the equation theta I minus 1j minus 1 plus delta x multiplied by BO number multiplied by theta ij, that will be equal to 0. Similarly, at y equal to 1, if I write, I will get this equation. Okay. So this is an iterative solver. So I need to put some stopping criteria. So what we do, we put stopping criteria like that. At every equation, what we'll do, we will find the residue, and we will at last we will find the norm of the residue. And if it is less than some user defined epsilon, we will stop the program. Okay. Clear? Please respond. Okay, so give me just 1 minute. I am coming. Okay, just 1 minute. Give me. I'm coming from washroom. Hello. So I am back. Please respond whether you are able to hear me. Okay. Yeah. So what we'll do. So this is our governing equation and boundary condition, and how we are going to solve. We have also discussed it. So after we solve, suppose we have solved this problem. Let us assume that we have solved this problem. So how we'll know that our solution, what we are getting, is correct or not? This is known as the validation of the solution. Okay. Whether we are getting the correct solution or not, how we will know? So first thing that we need to check is that the model that we are using, whether the model is correct or not, whether the equation that we have built is correctly able to represent the physical problem or not. This is the first question. Second question is what? Second question is that some of the assumptions that we are making to develop the mathematical model. Okay. So like we have assumed what? We have assumed the constant properties, constant heat transfer coefficient H. We have also assumed the constant heat generation, etc. So are they okay? Are they are able to predict the solution correctly or not? Okay. So this is my governing equation. This is my boundary conditions. So how we can answer this question? The easiest way to answer this question, if we have the experimental data. Okay. If we have the experimental data, we can see the effect of this now, whether whether whatever the assumption we are making, whether that is correct or not. So we have the experimental data for different thermal conductivity values. Sorry. Suppose we have the experimental data for the heat generation. If in the wall, in this rod, heat generation is uniform, then our assumption is correct that we have taken a constant heat generation. If the heat generation itself is not uniform in the rod, then the assumption that we are making that heat generation is constant in the rod, which is wrong. Second thing can be, first thing is the model, second thing is the simulation, whether we are doing the simulation correctly or not. But here is the catch. We are never sure unless we have the analytical solution to say whether our simulation is correct or not. Okay, unless and until we have the analytical solution, we cannot say whether our simulation is correct or not. But the thing is, if we have the analytical solution, then there is no need to go for the numerical solution. If we are able to getting the analytical solution, why will go for numerical solution? So how to verify our solution? So we can verify the solution with some benchmark problem. What is benchmark problem? Benchmark problem can be an analytical solution, or that can be a well accepted numerical solution. Okay, from the literature. So this analytical solution kind of thing can happen when we are trying to learn the numerical. Suppose we are trying to learning the numerical methods. In that case, we deliberately take such kind of problem where we know the numeric analytical solution. So we solve numerically, then we try to match it with the analytical solution. If we are matching it reasonably, then it is correct. And second thing, what we do, we can take some well accepted numerical solution and match our data, our result with the well accepted numerical solution. Okay. So the numerical problem that we have considered was what? Heat generation. We have considered heat generation in a nuclear rod problem. So to solving that problem, analytical solution is quite difficult. So we'll consider some benchmark problem to have a feel of whether we are going correctly or not. So the benchmark problem here is selected is the homogeneous part of that equation, that is Laplace equation. Okay. So this Laplace equation with some boundary condition at x equal to 0, sorry, at y equal to 0, y equal to h. Similarly, at x equal to 0, x equal to L, the boundary condition is given. Okay. In that case, this will be the analytical solution that will come. We will not bother about how we get the solution. This is a solution that we will get if we go for the analytical solution with some values of A, B, C, and D, N. Okay. So what we can do in this case? In this case, we will solve this problem using Gauss-Seidel method. Gauss-Seidel method. Then what we do? We find out the analytical solution at that discretized points. Then we try to plot them together whether they are matching or not. Okay. Then after doing these two things, another important thing is what? Grid independent test. Any physical problem that we are trying to solve numerically, what we are doing? We are first discretizing the equation. By discretizing means we are taking some delta x and delta y to solve the problem. Okay. So this delta x and delta y was not initially in the problem itself. We have introduced this. So we need to check whether our solution is independent of the grid side or not. How we can do that? We select some delta x and delta y. We do the simulation. Then what we'll do? We will repeat the same simulation with delta x by 2 and delta y by 2 grid size. Okay. Then we see how much our solution has changed when we change the grid size from delta x to delta x by 2 and from delta y to delta y by 2. We'll repeat this process until we see very less or negligible change from the change in the grid. Okay, reducing the by changing the reducing the grid size. Okay, so this is what grid independence test. This is very essential when we go for the numerical solution. Then after doing the, so first we'll do the grid independence test. Then we will plot that the result with respect to the benchmark solution. Sorry, benchmark problem. And that we'll do at worst possible places. Okay. Suppose we have this domain. In the core region, that may be there will be very less gradient. In that case, maybe our solution, our solver able to predict the values correct, but close to the boundaries, maybe it was not able to predict the values correctly. So what we'll do, we will try to see whether at the worst position place, whether our solver able to predict the value correctly or not. If yes, then we will go ahead. Okay. So that problem was what? That problem was steady state heat conduction with heat generation. Okay. So now we'll see unsteady heat conduction. So unsteady heat conduction, what will the equation? 1 upon alpha del U upon del T, that will be equal to del 2U upon del X square plus del 2U upon del Y square. Okay. Same kind of grid we are having. But in this case, there will be a time grid or time domain in the normal to the screen. Okay. So this unsteady problem can be solved either using the explicit scheme or implicit scheme or Crank-Nicolson scheme, as we have seen in the 1D case. Okay. Suppose I am using the explicit scheme, then in that case, this del U upon del T can be written as Uij at n plus 1th iteration of time minus Uij at nth iteration of the time divided by alpha delta T. Then these gradients we are writing at nth time. Okay. And what we are doing here, we wish to find the value at n plus 1th time. So if we are writing here in this gradient in nth time, what will be? These values are already known. These values are already known. Na? So if we convert this equation, we will get Uij at n plus 1th, that will be equal to Ui at nth plus Ui at nth at different grid points. Okay. So RHS is what? RHS is completely known. Na? RHS is completely known. Only LHS is unknown. LHS is unknown. So our RHS is known. So what? We do not require any solver to solve this problem. We can directly put the values here, known values, and get the value at n plus 1th. Suppose we have made some initial guess all 0. So we'll put this zeros value here to get the values at first time. At if we put n equal to 0 here. Okay, then we'll go ahead to next time. Then at the previous time we already know the value, so we will put the value here and directly calculate the value. Okay. So this is explicit scheme. If we go for implicit scheme, then what we'll do, we will write this derivatives. We will write this derivative at n plus 1th time. Okay. So this will be the same case, but here all the u's will be at n plus 1th time. Okay. So then what we'll do, all this u at n plus 1th time will bring back to LHS, and at nth time we'll bring them to RHS. Okay. So this is what? This is a pentadiagonal matrix. Huh? This is a linear equation that will lead to a pentadiagonal system of linear equations. So here, if you do that, these all the values that you will get. Uij minus 1, that will be equal to ui at j plus 1, that will be equal to alpha delta t upon delta y square. Similarly, ui minus 1j will be equal to ui plus 1j, that will be equal to the same value, but delta y will be replaced with delta x. And aij, these are a, no, you, not you, these are a. So aij will be equal to minus 1 minus 2 alpha delta t upon delta x square minus 2 alpha delta t upon delta y square. Okay. These are for interior points. No? So we have seen this for interior points because we have discretized the governing equation only. Now what we'll do? So here you can see that we lead to a pentadiagonal system of equation for n plus 1 at time. Okay. At 1 plus 1 at time. Means what? Means what this partial differential equation is converted into a system of linear equation, which is what? Pentadiagonal. No? Pentadiagonal. Pentadiagonal. So what we need? We need the Gauss-Seidel. We need the Gauss-Seidel algorithm at each and every time step. Okay. Clear? Similar to the implicit scheme, we can go for Crank-Nicolson scheme. What we'll do in Crank-Nicolson scheme, we will write this Laplacian that will be equal to half of Laplacian at nth iteration plus half of Laplacian at n plus 1th iteration. Okay. You can go by that. You'll see that will lead to the same pentadiagonal type of equation where some different aij values. Okay. Means what? This also can be solved by using the Gauss-Seidel at every time step. Okay. Clear? Please respond. Hello. So I am assuming that it is clear and I am audible. So let us move ahead. So what we have seen when we in last week when we are doing for 1D heat conduction problem, unsteady 1D heat conduction problem, there we have solved it using the Thomas algorithm. Means what? Tie-diagonal system, tie-diagonal solver. Okay. So is that possible to use the same kind of Thomas algorithm or tie-diagonal solver for the multidimensional case? That can be done using the alternative direction implicit method. Alternative direction implicit method. How this can be done? Suppose we have this governing equation. Okay, 1 upon alpha del u upon del t, which is equal to del 2 u upon del x square plus del 2 u upon del y square. What we will do in first step? In the first step, we will write 1 upon alpha del u upon del t. We will go from n to n plus half. Then we will go from n plus half to n plus 1. Okay. When we will go n plus n to n plus half, there we will use del tu upon del x square at nth only. And similarly here, we will use del tu upon del y square at n plus half only. Okay. And other one we'll assume as an implicit method. Okay. So what we are doing, this we are discretizing from n plus half to n. And this del 2 u upon del x square, I am assuming at n plus half iteration, n plus half time step. But this we are considering at nth step, which means what? This is already known. So if you discretize this, this is what you will get the equation. Okay. So in RHS, you will get some u terms at nth iteration. Okay, this is what this is known. But here this is at n plus half time, which is what unknown. So this is unknown. But if you see here, here is one term, here is one term, here is one term. All other terms are 0. Okay. So this is what? This is a tridiagonal system. This is tridiagonal system. No? So this tridiagonal system can be solved using the tridiagonal solver to find uij at n plus half iteration. Okay. Then in second step, we'll find uij at n plus 1th iteration. Okay. In that case, what we'll do, we'll go from n plus half to n plus 1. And in that case, we will use del 2u upon del x square and at n plus half iteration. But this we'll use at n plus 1th iteration. So this is what unknown. No? This is my unknown. So by using the Thomas algorithm twice, we can solve the multi-dimensional 1D multi-dimensional heat conduction problem using the Thomas algorithm. Okay. So this is the trigonal equation we will get. This is already known. These are the coefficient. So combining the step 1 and step 2, we can solve the partial differential equation using the TDMA. So in this case, the iterative solver can be avoided. Okay. Now we'll see the stability. So this stability analysis can be done using the von Neumann stability analysis, like we have did in the last week. If you do that, what you'll find that this explicit scheme is what? This explicit scheme is conditionally stable. This is conditionally stable. This is conditionally stable. Okay. So this is the condition for the stability that you will get if you do the von Neumann stability analysis. In 1D case, what we have got del t upon 2 delta x square. This is what we have got in the 1D case. So once we go to the 2D case, this delta x square is replaced with 1 upon delta x square plus 1 upon delta y square. Okay, that will be less than half. Clear? And these all schemes will be what? Unconditionally stable. Means what? It will be always stable. All these methods are consistent. What do you mean by consistent? Consistent means if we decrease this delta x, delta y, and delta t, if we decrease this, whether our solution converts to the exact solution or not. Okay. So all these schemes are consistent. So by doing the Taylor series X analysis, you can find the order of truncation error, delta x, delta y, and delta t to the power some n1, n2, n3. So this n1, n2, n3 will always come. That will always come positive. Means what? If you decrease this error will go to, this error will decrease. Okay. This ADI scheme is unconditionally stable in the 2D case, but in 3D case, it may be stable or unstable. In 3D case, writing this alternative direction implicit method is not very easy task. It is very complicated, but we'll not discuss that here. Okay. So this is what has been discussed in week 9. Okay. So we have revised that. Now what we'll do, we will try to solve some small problems. Okay. Then we'll do one practice problem. From there, what we'll do, we'll take a problem, partial differential equation. We will discretize that. Then what we'll do, then we will try to write the pseudo code for that, for the case. Then we'll try to write the computer program. Okay. So you please now respond in the chat box. What will be the answer of the question? So this is the question number 1. If the BO number is defined as HL upon K, then H will be what? L will be what? And K will be what? So we have just discussed this BO number Then H is what? Convective heat transfer coefficient. Na? This L is what? This K is what? Thermal conductivity. PVT. This is what will be this L? This L will be, rather than saying length, we should say length scale. Length scale. Okay, this is length scale. Yeah. So now we are moving toward the second problem. Second problem is what? For 2D Laplace equation, del 2, this is what Laplacian of u equal to 0. We are solving for u x comma y with specified boundary condition at the boundary. Okay. So what we do, we will discretize this equation using 100 comma 100, 100 cross 100 uniform grid. Okay. That will lead to some system of linear equation a u equal to b. If you do that, in any row of A, maximum non-zero term can be. How many number of non-zero term can be present? Maximum 5. Okay, good. 5. Now next question. While solving the linear equation A u equal to B using the Gauss-Seidel method, in every iteration, what will be the option will be correct? Matrix A will be updated, but the vector will be remained unchanged. Matrix B will be unchanged, but A will be unchanged, but B will be updated, or A or B will, both will be unchanged, or A and B both will be updated. Okay, both will remain unchanged. Good. Now next question. While using the ADI for solving 2D unsteady diffusion equation, ADI generally uses the diagonal matrix solver or pentadiagonal matrix solver using the Gauss-Seidel method. ADI uses explicit techniques or Jacobi iteration. Diagonal will be ADI. What we do in ADI, we do go for with two steps. First, we go from n to n plus half, then we'll go from n plus half to n plus 1. Okay. Next problem, 2D unsteady diffusion problem. Explicit scheme is what? We have seen the explicit scheme is what? Conditionally stable. No? What was the condition for the stability? Alpha delta t upon half. Oh, I forgot. Huh. Delta x square plus I forgot the value. Yeah, this should be less than half. No? This should be less than or equal to half. Okay. Now, next problem, implicit scheme, unconditionally stable. Crank-Nicolson scheme, unconditionally stable. ADI scheme in 2D case, ADI scheme in 2D case, ADI scheme in 2D case is unconditionally stable. Now one thing we need to discuss here. Okay, so suppose we wish to solve del 2u upon del x square plus del 2u upon del y square is equal to 0. This problem we wish to solve. Okay. So this can be solved using the Gauss-Seidel. So this equation we can convert into 1 upon alpha del 2u upon del t square will be equal to del 2u upon del x square plus del 2u upon del y square. Then we will solve this equation. We'll solve this equation up to steady state. So whatever the solution of this equation at the steady state, that will be the solution of this problem. Correct? So on the basis of that, we have next problem, Laplacian in 3D, which is solved for u, x, y, z with u, x, y, z are specified at the boundary. Then the unsteady Laplace equation solver can be used to solve the above problem. Second option is unsteady Laplace equation solver cannot be used to solve the equation, solve the above equation. So this can be used to solve the equation, but this is not the other way around. If we wish to solve the unsteady problem, then this unsteady problem cannot be solved using the steady solver. So unsteady problem, steady state problem can be solved using the unsteady solver, but the unsteady problem cannot be solved using the steady state solver. Clear? Now we move towards the practice problem. So in the practice problem, we need to write a computer program to solve this Poisson's equation del 2 to u upon del x square plus del 2u upon del y square plus 1 equal to 0. Okay, this equation we wish to solve. We have the specified boundary condition u at x equal to 0 and u at x equal to 1 equal to 0. Similarly, u at y equal to 0 and y equal to 1 is 0. Okay, we will use this delta x and delta y equal to 0.01, means what we'll consider 100 small steps here to solve this problem, steady state problem. This is a steady state problem because we do not see any time derivative here. But we want to solve this problem using the Crank-Nicolson scheme. This Crank-Nicolson scheme can be used for unsteady problem. Na? Unsteady problem. This is used to solve unsteady problem. Okay. So we will use the unsteady solver to solve a steady state problem. So what we will do first, we will convert this equation to 1 upon alpha del u upon del t equal to del 2u upon del x square plus del 2u upon del y square plus 1 equal to 0. This equation we'll consider. We'll assume some value of alpha. Okay. We will assume sub u initial, means at time t equal to 0, comma xy. We'll assume some value. Okay. This we will assume. Then we will solve. We will solve till steady state. Okay. Steady state. But means what we'll do at every time we will use Gauss-Seidel iterative solver. Okay. Okay. So how we can solve this problem? First, what we'll do? We will discretize. We will discretize the governing equation. Okay. Then we will, here we need to assume some delta t also. Delta x is already given in the question, but delta t is not given. So we will assume some delta t. Okay. But we will discretize the governing equation. Then we will discretize the boundary condition and initial condition. No, there will be no need to discretize the initial condition. We will discretize the boundary condition. Then what we'll do? We will, by doing this, we will convert this EDs to a system of linear equations. This system of linear equation will be AU equal to B type of formula. Okay. Then what we'll do? We will use this at every time step Gauss-Seidel iterative solver to solve the problem. We will do till we reach to the steady state. Means what? At some point, U old minus U new. If we find U old minus U new, if this values, if this value, if I take the absolute value of this, absolute value, if this goes some less than some epsilon user defined value, at that point I will stop. Okay. Clear? So let us see how we can solve this problem. So to solve this problem, first we will consider we need to solve this using the unsteady solver. So we consider this partial differential equation with this initial condition, u initially at 0, and this boundary condition. Okay. At ut greater than 0, u at x equal to 0 and 1 is 0, and u t greater than 0, u at y equal to 0 and 1 is 0. Okay. Now here we are considering delta x and delta y is equal to 0.01 and delta t equal to 0.02, 0.001, 0.001. Okay. Alpha, you can take any value, but here I am assuming 1. This we can define in the program. We can change the alpha value to get the solution for different alpha. Okay. So using the Crank-Nicolson scheme, this will be the discretized equation. So del t upon 1 upon alpha del u t upon del u upon del t can be written like that: u I j at n plus 1th iteration minus u I j at nth iteration divided by alpha delta t. Okay. Now this del 2 u upon del x square will be written as half del 2 u upon del x square at nth iteration plus half del 2 u upon del x square at n plus 1th iteration. Okay. So if I write in the discretized format, this is what I will get. Okay. So u I minus 1 j at n plus 1th iteration minus 2 u I j at n plus 1th iteration plus u I plus 1 j at n plus 1th iteration divided by 2 delta x square. Similarly to that, we will also get but at nth iteration. Similarly for the y del 2 u upon del y square, we also write del 2 u upon del y square also we can write similarly. So this is what we will get, this term and this term. Okay. Plus 1 will remain same. Okay. Now what we will do here, now what we will do, this whatever the terms at nth iteration, the terms at nth iteration means what? The known term. The known term will kept on the RHS and the unknown terms will kept in the LHS. Okay. So this is what my known term. So first what we will do? First what we will do? This alpha delta t I will multiply in the RHS whole term. Okay. Then what we'll do? This term will take into the LHS and all the terms will take into the RHS nth term. Okay. So if you do that, we'll get the RHS. RHS will be what? From here we will get minus uij at nth iteration plus this term multiplies by alpha delta t. If that will come into the LHS, that will give me alpha delta t upon 2 delta x square multiplied by ui minus 1j minus 2 uij plus ui plus 1j at nth iteration minus similarly alpha delta t upon 2 delta y square uij minus 1 minus 2 uij plus 1 at nth iteration minus alpha delta t. This alpha delta t multiplied here, this will become alpha delta t. If you take this to this side, it will become minus alpha delta t. Okay, this is what we get. So if I write this equation now, I can write like that. Na? This is a pentadiagonal system with a I j minus 1, u I j minus 1 at n plus 1th iteration, u I minus 1j, a I minus 1j at n minus n plus 1th iteration, plus this term, plus this term, plus this term, that will equal to dij. Okay, so this dij I am saying as d, simply d. Okay, and this ai j minus 1, that will be equal to aij plus 1, that will be equal to alpha delta t upon 2 delta y square. I am simply calling it as a. Okay, similarly, if I write ai minus 1 j, ai plus 1 j, that will be equal to alpha delta t upon 2 delta x square. That will be equal to c. I am just saying c. Okay. Similarly, if I write aij, this will be equal to minus 1 minus alpha delta t upon delta x square minus alpha delta t upon delta y square. I am simply calling it as b. Okay. This b will be equal to what? Minus 1. From here, if you see minus 1, here will be a minus sign, minus a plus c. Okay, so b will be equal to minus 1 minus a plus c. So this is the equation that we got here. Clear? So we have found out the boundary condition is same since it is specified boundary condition. So u, if I write u uij will be equal to 0 if I equal to 0 or nx. Similarly, uij will be equal to 0 if j equal to 0 or ny. Okay, this will be my boundary condition. So we have discretized the equation. So now we'll see how to solve this problem. We'll see its pseudocode. Okay, so I am defining some u new as initially 0 and u old as initially 0. From here, I have defined my initial condition. Okay, so I am going into the time step n equal 1 to some maximum time iteration, or I can directly use while some error in time is less than epsilon 1. This epsilon 1 is user defined for time. While this is less than or sorry, this is while this is error is greater than or equal to epsilon 1, I will do this. Okay, first I have defined u new. Simply I am writing u new to as u new as u. So first what I have done, I have defined u as a old value. Okay, then what we are doing, we are going for a Gauss-Seidel iteration. In Gauss-Seidel iteration, this sum is for the ri values. Okay, summation of ri square values. So I have defined sum equal to 0. This a, a, b, a, c, b, these are not changing with the grid points. No? So that's why I have defined this a, b, and c before the for loops for the grids. Okay, a, b, c I have defined here. Now I will go for the interior points only. Since already I know the values at the boundary 0. So I equal to 0 to I equal to 2 to nx minus 1. Similarly, j equal to 2 to ny minus 1. First, I will find out the d value. D will be some function of u old. So u old is already known. So I will find out this. Okay, d. Then once I get the d, I will find r. That r will be equal to d minus whole term. So this equation, what will the residue? Residue will be equal to RHS minus LHS at previous time step. So this will be my residue. So my correction will be what? Correction will be residue divided by B. B is what? Coefficient of Uij. Uij coefficient is B. So I will divide with B. Now what will be my Uij? Uij will be what? previous uij plus correction. Okay. Then I will define sum will be equal to, initially the sum was equal to 0. Now I'll define the sum will be equal to sum plus the residue square. Okay. This I will do for each and every, grid point. Okay. Each and every grid point. And once I have done all this, I have calculated, I will calculate the RMS, that will be equal to under root of sum divided by nx multiplied by ny. Okay. Then I will check if this RMS, is less than epsilon for the Gauss iteration, then I will break. Otherwise, I will do till I converge. Okay. Now suppose I have done for the one case, one time step. Now, before moving to the next time step, I will find out the error. That error will be the maximum value. You can define in this way also. Norm case, you can define like that also. Maximum of absolute of u minus u old. If this is my error, if this error is less than or equal to epsilon for the time loop, then I will break. Okay. So this is my pseudo code. Are you able to understand whatever I have told? I have shown here. So now what we'll do, we will write the computer program for this equation. Okay. So before doing that, if it is possible, please write this thing. No? Please write the expression for D. Where is D? Where is my D? This is my D. No? So we need to write the expression for D. Expression for D, expression for A, and expression for B. Arey yaar, why it is not working now? Okay. So this A, B, A, C, B, D. These are four main expressions. Okay. So now I will stop sharing from my iPad. Now I will start share from my computer. So what we need to do? First we'll solve this problem, then we'll plot the contour at steady state, and then we'll try to plot the temperature profile at y equal to 0.5. Okay, in the middle. So let me share. So this is the code I have already made, but I can write here again. So first what we'll do, we will discretize the equation. Na? I will see if I am able to make this program in half an hour. Hello. Okay, okay. So I'm audible. Okay, so now we need to define what? We need to define this A, E, C, D, R. Okay, so we will go to our notes and see what is the value of A. So A is what? Alpha. A is what? Alpha multiplies by delta T divided by 2 multiplied by delta Y. Delta Y multiplied by delta Y. Okay, so this is my A. Similar to this, what will be my C value? Only delta X will be replaced by, sorry, delta Y will be replaced by delta X. So this is my delta X. Okay. Now I need to define the B. B is equal to -1 minus alpha delta T divided by delta X square minus alpha delta T delta Y square. That was equal to -1 minus of A plus C. So I will control X. I will define the B here. B will be equal to -1 minus A plus C. at what, comma, j minus 1 plus b multiplied by 2 minus 1 comma j plus b multiplied by 2 I comma j plus, and this one will come again, control C, control V, but here rather than j minus 1, we will have j plus 1, where we will have I plus 1. Okay. So this is what my, this is my R. Now what will be my correction? Correction will be R divided by B. Okay. R divided by B. Then I will define U new Ij will be equal to U new plus correction. Then I will define sum will be equal to sum. So I have written down the program. Okay. Now after this int, what I will do? I will plot it. Na? I will do the plotting. Plotting of what? First, I will do the contour plot of U, contour plot at U at steady state. How we can do that? Simply I can do contour I can do directly contour f x comma y comma u new. I will do that. I will get the contour. Now I need to plot the temperature profile. For that I need to open a figure. So suppose figure 1. Then I need to do what? I need to plot the temperature profile at y equal to 0. So temperature U profile at y equal to 0.5. Okay. So for how I can do that? I will find some t. That t will be equal to u new u small u new at every point at every I, but at every I, but at, suppose at 50th means what? At n y minus 1 divided by 2th location. So by doing that, I can find out the t. Once I have found out the t, I have found out the t, I simply do the plot x comma t. Okay, then it will give me the plot. So simply what I need to do, I need to save this program. Suppose this is my week 9 program. Okay. So if I run this program, so here also I have made this program. So suppose I am running it now. Suppose I have run this program. So it will take some time to run. Okay. So this is my temperature profile at steady state condition. This will be my temperature profile at y equal to 0.5. Okay. So this is the temperature profile. This is my contour. Okay. At steady state condition. If I want to see temperature, sorry, if I want to see the temperature contour at different time in the different time step, I can also see that. How I can see that? Let us see. So let me just run it again. So one in this machine. So very close to the iteration, very at initial times, temperature is almost uniform everywhere. It is zero, around zero. Okay. Now I have increased the time step. So it is now showing 0.04 in this region, and more and all other region it is less than that. Okay. Then I increase the time step further. Then what we see here, we see now temperature profile in this four region is 0.07. Other region is less than that or greater than that. Sorry, less than that. Now I increase the time step further. So this four region, higher temperature region is what? Increasing. No? So this is that steady state. If you see here, this is almost same. No? This is almost same at steady state. These are the steady state data. And if you see here, it has increased a bit. The higher temperature region has increased a bit. Here you can see that. This is the temperature profile at y is equal to 0. Okay. Here, the plotting that you can search how to plot contour plot in whatever language you are doing, then how to add the title in the figure, how to maintain the aspect ratio of the figure, then how to give the x label, how to give the x tick, how to give the y tick, how to plot line plot, contour plot, then how to plot an image like that. No? The main part was here to discuss was the algorithm. So that I have tried to make here. With the plotting part, I have already done that. That I have shown simply by running that. Okay. Maybe how I have written the program that maybe help you to think how to write the program in a right pattern. First, try to write a pseudo code, then go to the computer program. While writing the pseudo code, sometimes we make some mistakes that we are able to rectify when we are writing the program. Okay, sometime in the pseudo code, because in pseudo code we do not see how the program is going. Sometimes we make some mistake. But while we writing the program in the computer, if there is something wrong, you will never get the right solution, or your solution may not converge even. So you may run your program for 1 hour, 2 hour, 3 hour, but it is not converge. It means what you are making some mistake. So it is a good practice to add some maximum iteration kind of thing. I have written directly while E1 is less than that. You can put another one more condition, maximum number of iteration. Suppose you have defined it as maximum iteration of in time equal to 1 lakh. So in time, it can go up to 1 lakh iteration. Similarly, in Gauss-Seidel, it can go up to 1 lakh iteration. Okay. Then you define some elementary variable K1 and K2. While this K1 is less than or equal to maximum iteration in time, and while this K1 is less than, while this K2 is less than maximum iteration in Gauss-Seidel, you perform this the whole iteration path. Okay. Clear? Okay, so I am now stopping the screen. I think I'm stopping the recording.